Right, so let's get going. So I left my simple beam. So we want to look at how to avoid that type of failure, which is called simple elastic instability. So that's where you apply an axial compressive load onto a beam. So we've seen there. So we want to avoid. Talk to me. Thank you. Just give me 50 minutes. Right, so what we want to do, we want to avoid that from taking place, and I showed some few very nasty pictures, which I will show again, because it's very important to try to understand why we need to make sure that we don't have that. You can see that you don't want to be designing a building where that is taking place, and you don't want to design a building where that is taking place, and you don't want to be on the train that is going on that. So what we want to show now is what is the load that is causing that to take place, and you want to make sure that when you do your design, you make sure that the design load is less than that. So you don't get to that particular value. So that is the shape of the structure when the load has reached that value that is causing that type of failure. It is that magnitude of the load that we want. As we can see, it has bent. So it has bent that way. And I showed yesterday that if I turn that this way, it's very similar to a beam in bending, but now the load is coming from this side. So we will work out what that load is, and to make sure that we don't get there. So if we were to make a cut right there and look at what happened to the reduced structure. So this is like our free body diagram. So that's like a free body diagram. So can I just change that? That is the wrong direction. The direction should be like that. The direction of the moment should be that way. So if we have that, so we can look at what is the magnitude of that bending moment as a function of that load P, and as a function of that movement that we get. So the movement we've denoted by V, and is at a distance x from our reference. So that point there is the origin of x and y. So if we look at the magnitude of the bending moment, what is the bending moment? What is the moment of P about point Q? So what's the bending moment of point P about point Q? So the P in blue. Okay, so that is a line of action there. And we want to take moment about point Q. What should be that moment? How do you find moment?
0.
0?
Mm-hmm.
Yeah?
Mm-hmm.
Okay. So what is the definition of moment? Moment is the product of the force and the distance between the line of action of the force and the point about which you are taking the moment. So my force is point P. So we have that acting downwards. We have that acting P, and that distance here is V. So what is the moment? So if you have P downwards, P upwards, and the distance between them is V, what is the moment? P times V, because this is going to cause a rotation that is going to do like that. So the bending moment about point Q, which I'm going to write here, I will say M around point Q is P times V, where V is the magnitude of the movement of that structure at point Q. Remember, our aim is to find the value of P that is going to cause that type of failure mode. So, and you will see it's not a very long derivation. So we are assuming that V is very small. So I'm going to substitute, instead of M, I'm going to put load P and the magnitude of the movement V, and I'm going to do the integration and find what P is. So we've got our final solution. So let's do that. So if I put that in our bending deflection equation, I now have that. So I'll put my instead of bending moment, I'll put P times V. So I'm going to rearrange that. I'm going to bring PV to the left hand side. I'm going to say I now have d2V dx squared plus P over EI times V equals 0.
Excuse me, the previous slides, M was
Sorry?
previous paper.
Yeah?
Was it M equal minus PV?
No, so M equals PV.
Thank you.
Okay. So if I look at that, I want to solve that for V. So the details of the solution, I'm not going to go through, so I'm going to just explain how it is done. So this can also be written as d2V dx squared plus lambda squared V equals 0, where lambda is P over EI squared. Okay. So I've replaced P over EI because that will appear in the solution. Now I want to solve equation 4.3, second order differential equation in V, which we can integrate and solve. So if we try to do the solution, we're going to end up with something like 4.4. So I'm not going to go through that. You did, I certainly hope in your EG 3007, you've gone through how to solve second order differential equation. Let us assume now that that is correct, which I think it is correct. That is the solution of the movement of the beam due to load P that we've put in, and that load P is appearing in the solution through the parameter lambda there. So now we have two unknown constants because it's a second order differential. So that's why we have two unknown constants there, and we want to find what those two values are. So I'm going to go back to the diagram, and I want you to tell me what boundary conditions we need to be able to find C1 and C2. If we go back there, hope that shows. So that is the deformed structure. That is the origin. At this point, x equals 0, and at that point, x equals the length of the beam L. And it is pinned. So what is the deflection that we know are two locations that will allow us to find those two, C1 and C2.
Zero A and B.
0 at,
A and B.
so 0 at A and B. So V will be 0 when x equals 0, and V has to be 0 when x equals L. So if we use those two boundary conditions, so we'll say number 1, V equals 0 at x equals 0. So if we're to do that, so if I put that into that equation, so 0 equals C1 cos 0, which is C1, and plus C2 sine 0, which is 0. So what we now have is that I have 0 equals C1 plus 0, which implies C1 equals 0. Yep. And I'll go back to the second one, and I'll say my second boundary condition is V equals 0 at x equals L. So now we know that C1 is 0. So I'll put x equals L in that equation, and I will say, so V, which is 0, equals C1 is 0, and I'll have 0 plus C2 sine pi L.
Excuse me.
Yeah.
What is this lambda?
Sorry?
What is this lambda?
What is lambda? Lambda has been defined here. Lambda, because we don't want to be writing P over EI.
Oh, so it's just a symbol referring to all of that.
Yeah, so lambda is denoted as P divided by Young's modulus divided by I, everything, and then you take the square root. Okay. You will say, so towards the end now we will drop that one because we want to find P.
But does it determine the value of cosinus and sinus, right?
Sorry?
Does it determine the value of cosine and sine?
Yeah.
So it's sine of lambda x.
Yeah.
Or, not, or sine x of x times lambda as a separated component.
I'm lost. I'm
So
totally
you have
lost.
a cosinus and sinus.
Yeah,
So
yeah,
it's cosinus of something.
yeah.
So lambda and x will be in the brackets.
Yeah,
together.
oh yeah, yeah, yeah. So, okay, if this, that's what you have here,
Yeah.
lambda here, and lambda there. Okay.
Thank you.
Right. So now we know C1 is 0, C2 is not 0 according to that, is C2 sine lambda L. So therefore we'll say that, which means from that one, we say that C2 sine lambda L is 0. But because we know C1 is 0, so which means the first part of this deflection equation here is 0. So for the second part, because we know the beam, that structure will have deformed, so C2 cannot be 0. So C2 is not 0, but we'll say, therefore, it means that this one here, that sine lambda L would be 0. If the sign of something is 0, and we know from our trigonometry that is 0, that is pi over 2, that is pi, that is 3 pi over 2. If you are taking the sign, we know that sine 0 will be 0, sine pi is 0, sine 2 pi is 0, sine 4 pi is 0, and then you keep going. So if sine lambda L is 0, it means that lambda L is either pi, or 2 pi, or 3 pi, or 4 pi, or 6 pi, like that. So now that we've shown that, so we can now say that our lambda, which is what we're trying to find, is some value of n, which could be 0, 1 pi over n. Where n is either 0, or 1, or 2, or 3, or 4. Okay. Because we define our lambda earlier, that lambda is p over ei square root, then it means that if I square both sides, I can find p. So, and that's where we've got here. So the load P that will cause that beam to become unstable, now we'll be able to find. So what this shows is that it's not just one value of P, because the first one is when n equals 1, the second one is when n equals 2, the third one is when n equals 3, and so you have different values of load that will cause that type of failure for a beam that is pinned at both ends. But if you are slowly increasing your load from 0, and you are ramping it up slowly until that failure starts, the load that will cause that failure is the P that has the minimum value. So the first one is when n equals 0. We know P will not be 0. So the minimum value that will cause failure is when n equals 1. So when we are designing a structure that is pinned at both ends, that is subjected to load in compression, then we have to evaluate the value of P here, and now make sure that the design load is less than that. So when n equals 1 is the main major critical load that we want to make sure that we don't get to. So our critical failure load for a structure that is pinned at both ends, that is why I underline this, because the solution is based on that. So it is pinned at both ends, then so we'll be able to determine that. So we have E, which is the Young's modulus, and I is the second moment of area, and that is based on whichever axis the beam is bending about. I don't have anything to use here. So you will see in the next slide. So now that I've got that, we know we can find how it will deform, which I've given here. So I will explain that next. So if I have a cross section which is like this, the question which we will normally ask is that we know this is the load that will cause that failure, but in which direction will it bend? Will it bend about that axis, or will it bend about that axis? And the same thing for an I-beam, will it bend about this, or will it bend about that? Because if you look at that bending could be this way, or it could be that way. And that is mainly what that is saying. So what that means therefore is that when we're doing this, we have to calculate that critical load for the value of I about that axis, and the value of I about that axis. And then, so we then decide which one has given us the minimum value, and that is the direction at which that beam will fail. So let's see whether you still remember how to find the second moment of area for that. So let's look at the first one. We want to find the second moment of area. Let me say that is B, and let's say that height there is H. So for the first one, rectangular, what is I about 1, 1, and what is I about 2, 2? So what is I value about, if we are taking segment of area about 1, 1, 1, 1 axis, what should that be?
BH to the power of 3 divided by 12.
BH to the power of 3, so 1/12 of BH to the power of 3. Okay? And what is that? What is the segment of area about 2, 2?
HB to the power of 3 by 12.
Sorry?
The opposite variables. HB to the power of 3 by 12.
Okay? So that will be 1/12 HB3. Okay?
Is that correct?
Yeah. So everybody, you should be able to find the segmental area about any given axis, because you need that to be able to do this. Because you need to be able to determine whether your load, which is going to cause failure, about any of the axes. Okay. So we have that. So let's do this second one for the I-beam, for the I cross section. So I'm going to just put, and let's call this width B. It's the same one at the top, that is B. We call the total depth up to the base. We call that D. We call this height here dW, and we call this thickness here TW, and the thickness here T flange. Okay, so the top is width of B, and this depth here is D subscript W. D subscript W. W means the web. So, and the thickness of the web is TW, and the flange, which is this one and that one, the thickness is TF. Right. So, what is I about? What's the second moment of area about 1, 1 axis? Who's going to make a guess? Okay, let's do it together. So the way to do that, when you have that, is to, so we're going to assume that we have a complete rectangle like the one on the left, which is that all the way down, and then take away the I for the one at the inside. If I look at the complete triangle, I will have 1/12 B D cube. So that is assuming that I have a complete rectangle, but I know I don't have a complete like that. And I'm going to take away what is left. I will say I have 1/12 of B minus TW times DW cube. see if you can get that, okay? So you look at the whole as a rectangle, and then you take away the ones that you know you don't have any material in. If I do it for 2, 2, it will be exactly the same. We write it down as we've done for the first one. That will be 1/12 of dBW. Okay, so we've taken that as a complete rectangle, and then I'm going to take away what is left. That'll be 1/12 dW B minus TW. Okay. So if I have a structure which is in compression and is made of an I-beam, then I will have to determine this based on an I value about 1,1 and I value about 2,2, and then whichever one gives me the lower value of load, I will say that is the load that will cause failure, and that is the direction along which it will fail there. But sometimes you don't get that type of failure because you are increasing the load in compression. That structure might yield before it actually fail by unstable failure. So in that sense, we want to compare what will be the stress when that critical load is acting on it. You can work that out, where A there is the total area of the cross section. If you are dealing with rectangular cross section, is the total area here. If you are dealing with an I-beam, is the area of that shaded bit. That will tell us what is the stress that you have. If that stress is less than the yield stress of the material, then that failure will occur before yielding. But if that stress is more than the yield stress, this is the yield stress, let me just make that clear. That's the yield stress. So if that stress is more than the yield stress, then you're never going to get there because that structure will fail by non-linear plastic deformation. It will yield before it gets to that stage. So the failure mode then will be based on the yield stress, not on that type of that failure mode that we've just showed there. Okay, so is that clear to everyone? So what we've done so far, we've looked at a structure that is pinned at the base and pinned at the top. But that is not always the case. Sometimes you might have a structure that is fixed, built in at the base and pinned at the top, or fixed at both ends. So now we have to go do the same thing and look at what if my structure is fixed at the base, but pinned at the top. Okay, so, but before we do that, I want to just show a rough sketch of what the deformation mode will look like for pin structure. So let's look at that. So I'm going to just draw that like that. I'm going to assume I have. So the first mode will be something that does that, where that is the load P, that is causing it. So that's our first mode. That is our mode 1. That is the one where N is 1, and the critical load is pi squared EI all over L squared, where the length is this. So that's the one that has the minimum load. That's the one that will normally take place. But sometimes that is actually constrained from taking place. Then you might have the second mode where N is 2. So let me just show it's the same. Let's say that is the initial length. We have that as the N. If it is like that, you will have something that does that. So the load is acting here. Is acting like that. That is P here. N is 2, and P critical is pi squared 4 EI all over L squared. And that is mode 2. You can see because of the factor of 4. So in order for this to take place, you need 4 times the load that is required for this to take place. If you go to the third one, which can also sometimes happen, but not very, very, very common. So we'll do that. Let's say that's the end. That's the initial length there. So we'll have something that does that. And in that case, so we have the load is here, the load is here, N is 3, and the critical load is 9 pi squared EI all over L squared. And you can see that that is 9 times the value of the load that you require for the first mode. And that's why we always look at what load is required for the first mode to take place, because that is the one that is likely to be the main mode of failure. Okay, so, but remember I said, I think yesterday, about whether the beam is considered as short or as slender. So we're going to look at how we,
So is the coefficient just the square of the n?
Yeah, it's square of the n. If you recall, let me just put that here. We said just in period, maybe the critical is n squared, pi squared EI all over L squared. So that n is coming because of the sign, because sine 0 can be pi, 1 pi, 2 pi, 3 pi, 4 pi, like that. So now, let's go into how we decide whether this type of failure mode is likely to occur instead of the yielding of that structure. And that will depend on whether the beam is considered as being slender or as being short. And one parameter which we will need, one of them is what is called the radius of gyration, which I'm going to define now. The radius of gyration, which is defined there, is the ratio between the second moment of inertia and the area of the particular cross-section that you are dealing with. Put it here where A is the cross-sectional area. So from that, if I square both sides, my R squared becomes I over A. Which here means that I equals R squared times A. Okay. So that radius of gyration mainly is a measure of how far the center of mass, where the mass is concentrated, how far it is from the axis that you are taking I on. So if R is very small, it means that the center of mass is very close to that axis that you are using to calculate I. If R is very large, it means that the center of mass of the cross-section is a bit further away from that particular axis. So now I want to write my load, that critical load, in terms of the radius of gyration. So now that I've defined what that is, if you recall what we just said a few minutes ago, we said P critical, that is the minimum one for mode 1, is pi squared EI over L squared. Okay. For a structure which is paying at both ends, but now instead of I, I'm going to put R squared times A, and I'm going to write now, so that is now pi squared E R squared A all over L squared. Okay, so I've replaced, instead of I, I've replaced that with radius of gyration R squared multiplied by the area of the cross section. If I divide both top and bottom by R squared, I will get equation 410. Then we will get equation 410. So, which means if I know the radius of gyration, I can still calculate that critical load which I want without knowing what the second moment of area is. So from that. Okay. Are we all okay with that? Okay, so let's move on. So the next one. So if you look at that very critical there. Now, if I look at my stress, recall what we said about the stress. The stress now, when it first now becomes P critical all over area, which is now pi squared B all over L over R squared. So as I increase, I now say that critical stress depends on the ratio between the length and the radius of gyration. So I'm going to just make a rough sketch here that will define what short and slender is. Let's call that L over R. Let's call that stress. So if I plot stress against ratio between the length of that structure and the radius of gyration, so what I will get will be something that looks like that. So as you increase your radius of gyration, so the stress that you put on the structure will go down. But as that length over R gets smaller and smaller, the stress goes up. But you cannot increase the stress beyond the yield stress of the material. At some point, the material will start to yield. Let's just say the yield stress is here. Let's just say the yield stress is there. So the value of L over R that makes your stress you have equal to the yield stress defines what is short and what is slender. So if we are on this side, we will say we have a short beam. Therefore, it will yield first before it buckles. If we are on this side, we will say we have a slender beam, which will buckle first before it yields, because the load required to actually buckle it is less than the yield stress. If you are here, the load you require to actually buckle it is much more than the yield stress, so it will yield first. And that's how we define that there. Okay, so I think we're doing well. So yeah, so I'm going to move on to the next one. It's similar.
Wait, so one sec.
Sorry?
Right. Thank you.
Okay, right, so now we've done what happened if the two ends are pin. We're going to go through the same thing. What if one end is fixed? Which is not, probably this is much more common, because if you have a vertical structure here, for example, it will go right into the foundation. So one end is fixed, but the top might not be fixed. So if that is what we have, we want to find out what is the maximum load you can put on that structure. So we go through the same thing. So here it is fixed. Ask me. I know the answer, not your friend.
Why did we calculate the second moment of area before?
Sorry?
On the page, we calculated 4 second moments of area, and why was it relevant for this class today?
Because you need to know the direction along which the beam is going to actually buckle. So if you have that,
Yeah.
the beam can buckle about 2-2, which means it can buckle this way. Okay?
Mm-hmm.
Or it can buckle this way, if it buckles along 1-1. So you need to know that if that failure mode is going to occur, along which direction is likely to occur. And that will tell you whether you need to provide additional reinforcement. Okay?
So we have to calculate the buckling for different moments?
Yeah. So if you have any cross section, so that is not a square, you have to determine what is the buckling mode along the two major axes for that particular cross section.
Can we do an example of that?
Sorry?
Can we make an example, please?
Yeah, you will see when we get there. Okay, so let's finish all the theories first. Like, so if the beam is fixed at one end, then we go through the same process again. We look at how it's going to deform. The load is now being applied at the top. So when it buckles, that is the shape it will take. You can see because it is fixed at that end, so there is no movement and there is no rotation at that end because that is fixed. So at the top, it deflects and there is a bit of rotation as well at that end. So we go through the same thing. We write down our moment deflection equation, and we find out what is the bending moment at a given section. So I've taken a section, arbitrary section somewhere here, and we've drawn it there. We want to find relationship between load P, deflection delta, the maximum one at the top, and M. And we can show that is what we've got. So if you want, I can write that for you. If you look at the moment M there, M plus P delta minus V equals 0, which means M equals minus P delta minus V. So what we're doing is we are finding what is the relationship between force P and the bending moment at that section that we've got. We know the moment. We can put the moment in our bending moment and deflection equation, which is this, and then we can now just go through the same steps again. So let's see what we get there. So I'm going to open this up to make it easier. We have P delta minus P V. Remember, what we are calling delta here is the maximum displacement where the load is. Okay, so that is right at the top, and V is the value of the deflection as you go along the length of the beam. So V is 0 here, and V has got the maximum of delta where the load is. So now we have the same thing, second order differential equation, which I'm going to rearrange to be d2V dx squared. So I'm going to bring plus P all over EI times V equals P all over EI delta. So that is V. So then we do exactly the same thing. So we will replace P over EI as lambda everything square root, which is what we have here, and then we try to solve that. We do the first integration, we do the second one, and then we end up with the solution of V, from which we can find value of lambda, just as we did for the first one. So what do we get? So let me just quickly show that before we end. We get something which is similar to what we just done. We get something like that. We still have delta there, which is coming from the maximum deflection at the top. So now I have C1, I have C2, and I don't know what delta is. So I have three things there. So I need three set of boundary conditions to use. So I'm going to ask you to tell me what are the boundary conditions that I need if I show you the diagrams again. So here's what we have. So we have the equation for V, which is here. So we're starting from A up to B. So what are the boundary conditions? Boundary conditions are what we know about V and the slope. It is built in at A. Built-in means it's not allowed to move or rotate. If that's the case, V equals 0 when x equals 0. So that is at A. And the slope, the V dx is also 0 at A because it's not allowed to rotate at that point. And when x equals L, which is right at the top, V equals delta. And that is what we have from that diagram there. Let me write that down. So I will say V equals 0 at x equals 0. So if we put that into the equation, so what that we give first into that equation at the top, we have 0 equals C2 plus delta, because the first one will be 0, that will be C2 plus delta. And therefore C2 equals minus delta. And then I go to the second one, and I'll say, what do I know about the slope? The slope dv dx equals 0 at x equals 0. So if you differentiate dv by dx at the top, what do we get? If I differentiate, what is dv dx? So if I differentiate this, what do I get?
Minus lambda c cosine lambda x.
Minus lambda.
Minus lambda c1.
Oh, okay. No, it's not.
No, just plus.
No, it's okay. So it is plus. That's right. That's right. So we have c1 lambda cosine lambda x, and we have minus lambda c2 sine lambda x. And there's no delta because delta is a constant. Now if I put my x equals 0 there, so if I put x equals 0 there, what do I get? So cos 0 is 1, and sine 0 is 0. So if I do that, I will say dv dx at x equals 0 implies c1 equals 0. And then I go to the last one, which is the last boundary condition, which is v equals delta at x equals L. Now that we know that C2 equals minus delta and C1 equals 0, if you were to do that, what you will get is you will get delta C2 sine, you get delta cosine lambda L equals 0. We know C1 is 0, we know C2 is minus delta. So that is what we will get.
Excuse me.
Yeah.
Can you tell me why v equals delta when x equals?
So why V equals?
Why v equals delta when x equals L? Why is that?
Why is that?
Yeah.
Look at the diagram. So V is the magnitude of the deflection that way. So here it is 0, it's not moving. As you go up, it is increasing, and when you get to the top, it is that. Right, let me see what have we got. I've got 3 minutes.
So delta is the constant.
Yeah, delta is the magnitude of the deflection where the load is applied at the top, at the far end.
So it's the maximum deflection.
It is the maximum deflection for this one. Okay, so if we look at that last one, delta cos lambda L equals 0, we know delta is not 0 because the beam is actually deflecting at the end, which means cos lambda L has to be 0. So if cos lambda L is 0, what does that imply? Remember, we know that when you are doing your cosine, the cosine of 0 is 0. The cosine of pi over 2 is, the cosine of 0 is 1. The cosine of pi over 2 is 0. And the cosine of 3 pi over 2 is 0. The cosine of 5 pi over 2 is 0. And you keep going like that. So what this means, therefore, is that we have lambda L must be n pi over 2, where n equals 1, 3, 5, and you go like that. Similar to the one that we've done before, but we know lambda to be p over ei, and that allows us to find this. So therefore, we can say that lambda, which equals p over ei square root equals n pi over 2 over L. So which means we can now find our p. We take the square of both sides. We will end up with this. So the lowest value is when n equals 1. So we know we can have second mode, n equals 3, n equals 5, but you will get to the one with n equals 1 first, and therefore we will end up with something which looks like that. So if the pin is fixed at one end and also free at the other end, then we can find that load that we need.
You think,
Yeah.
how did you simplify the third boundary again, please?
So did I do what?
Simplify the third boundary,
Yeah.
that part on the right, that delta cos lambda L equals 0.
So you know that your C1 is 0,
Yeah,
so that is 0.
yeah,
Okay, so V equals delta. This one is delta.
yeah.
You have C2 cosine lambda L. Okay?
Yeah, plus delta and delta minus delta equals 0. That's why it's 0.
Yeah. No, it's not 0. It's delta cosine. Yeah, so you bring this delta back here, that becomes 0. Yeah. Right, so I think when we come back tomorrow, I will do 2 examples. We'll finish this first, and then we'll do two cases, and then we'll end this one here. Okay? Sorry? It's not tomorrow. I'm enjoying myself, that's why.
I think he gives a heart attack.